Hello everyone, welcome back. Today we'll be talking about a pendulum. We will go through a quick review on the harmonic motion, which we already know about, just what we need to address the problem, let's say, the scenario of the pendulum. In the case of, I will see the example in the small oscillation. In future videos, we'll maybe attempt to do the general case. At least we will see what equation will lead to, and then we will derive then the period of the pendulum, which is a well-known formula for the uh, for this scenario. Okay, so let's start with a quick review. So we know the harmonic oscillate. Well, we know the harmonic equation of motion, which is the second derivative of the displacement, which is x dot. It is equal to minus a constant omega square. I will show you why it's omega square, but it could be any constant. So let's say the important thing is that it's a positive constant with a minus and the displacement. Why the minus? Because we know that exactly we can see that the displacement is directly proportional to the acceleration, but with a negative sign, meaning that when we have an equilibrium, suppose a loaded spring, where a mass is attached, you can see that if you are pulling the string in this direction and you leave the mass go, the force will act in the other direction. Okay, so um, this is a very simple example that give you an idea of why there is this important minus sign in the harmonic oscillation, because the force is attractive towards the equilibrium point. Okay, so we have this equation here, which we know, and the physics that is behind of this equation tells us that the force is attractive. Okay, so if we want to, we need to uh, pull against the force to make a displacement, and then the force pull it back to the original point. Okay, so with that in mind, we can we can we can try to guess what could be a solution for this equation. We don't want to go. So this is a differential equation. So we should be using all the mathematical machinery that we know of about differential equation, but I don't want to do all the derivation with all the details. I just want to give you an idea of why this is called harmonic motion, and this equation here leads to an harmonic motion. So I can cheat a little bit and give you an ansatz, which is basically what I guess is a solution of this problem, knowing that I know already the solution and it can be easily guessed in this case. This is just a particular solution. It's not the most generic solution. The most generic solution can be find out in other videos where we solve the harmonic motion properly. But in this case, I want just to give you an example to understand why it can be thought as a harmonic motion. By the way, harmonic means it's a synonym of periodic motion, because we will see it. So it's a way to say that there is some periodicity in the motion. So if you think about an oscillating spring, the spring is going up and down with a mass loaded up and down periodically. So we are leading to the idea that there must be some periodicity built in the motion. And in fact, if we try with a periodic function, let's say a cosinus function, and we derive it twice, we get this exact formula here, because the derivative of the cosinus is minus sinus. So if we derive in time, cosinus omega t is omega minus omega sinus omega t. And if we derive it again, the derivative of sine is the cosinus. We don't change the sign, and then we get again the cosinus. So as I said, if we derive twice, sorry, this cos omega t. So if we derive it another time, we go back to this. The second derivative of cosinus omega t is equal to minus omega squared cosinus t. And this is exactly of the form x dot double dot minus omega square. And now you see why the constant is a square, because it's coming from 2 times the derivation of a periodic function. So it's just a convenient way to express the equation for us. It could have been done in a different way, but and then we would have discovered that the constant was the omega square. Omega is called the pulsation, and is very similar to is 2 pi over period, and is very similar to the angular frequency or angular velocity in a circular motion. But since this is a linear motion, we call it pulsation. But basically, it's related to the same concept, something that is periodic in time. Okay, let's move on. Okay, so here I made a mistake. We can take another one. We can take sinus. It will work the same. Sinus or cosine. In fact, a combination of sinus and cosinus will work the same as a solution, and even more general combination of this can work. So here I picked the sinus just to, as I said, just to lead you with the idea that an important thing is that is the solution of this equation is a periodic function in time. And then, as I said, omega is 2 pi over the period, because and the period is what we all know about the sinus or cosinus function. So let's pick the sinus. The periodicity is exactly the distance between 2 crests or two minima. So this is 0, this is 0, this is 0, and in fact this is the period, or this is 1 and this is 1, and this is exactly a period. So nothing new. The same goes for the cosinus. We can deal with it. So we have an idea of why we are dealing with that kind of equation, and why that kind of equation would lead to harmonic motions. Now we jump right into the example and of a pendulum. Okay, this is a very idealized pendulum. So why it's idealized? Because basically we have a fixed point, which is this one, and there won't be any force exert. So it's free to let the pendulum rotate, actually swing. It's not rotating. Well, it's rotating, but let's say swing. So there is no friction here, no friction. Okay, as always, and there is no air, so there is no drag in the force. So the only real force that we need to consider is F equal mg, the gravity pull towards the center. This is the mass of the object. This is the same pendulum in the position in the equilibrium position. So this is called equilibrium position, where the motion is at rest. The mass, the force of gravity pulls down, and then there is, of course, another force, because the force of gravity can be thought as decomposed into components, as we know. One is the tension in this direction, Ft, and the other is the Fg, let's say. f2, and this one is mg cosinus alpha, and alpha is this angle there, which is the same as this angle here. Okay, so this force here is counterbalanced by the tension of the cord. So we assume that that in this direction here, the two forces are the same. T is equal to F2. So there is no motion along the rope. It's not stretching. It's tense. It's fixed length. In fact, the length is the same. It's not a spring, basically, if you want. And the length is the same, and it's L. Even when the position is not in the equilibrium point. The second position, as I said, is not the equilibrium point. And what we want to do, once we know that the forces in that direction are the same, the only force that is acting on the mass is this force here, which is mg sinus alpha, because we know that the composition of the force in sinus and cosinus with respect to alpha. And what we want to know is this basically displacement s, or x actually, x, which is an arc of circumference. We will do some approximation to understand how to get to that displacement and to solve the equation of motion. Okay, this is an alpha. I will comment on alpha. Alpha cannot be too big, otherwise we will not make a simplification, as I will tell you in a sec. So just to set the scene, there is no friction, there is no air. The tension is equal to the force of gravity times the sinus, or times the cosinus of alpha, meaning that the rope is tense, is not stretching. At a fixed point lets the pendulum swing without any problem there. Okay, so we have only one force that we need to deal with, which is mg times sinus alpha. Okay, let's see where we. Okay, so we started from, as you said, the usual F equal ma. We simplify only to consider ft, the force along the oscillation direction, and then we know that the acceleration is equal to minus omega squared times the displacement x. We know that x is the arc, the displacement arc, which is a square, and we will make an approximation here. Okay, the approximation is that these two sides are different, okay, but the sinus of alpha for angle yes, and x is equal to L times alpha, as we know, because this is the relation between the length of the pendulum and the circumference. Okay, so we know that for small oscillation, so less than 15 degree, we can say that sinus alpha is equal to alpha. Why? We can make an example, 15 degree as an upper bound if you want, and we get sinus of pi 15 over 100, which is the conversion between degrees and radians, is 0.2588. And if we only consider the angle converted in radians, pi over 15 times 15 over 180, we get 0.2617. It's roughly 1% error. So of course, if the angle is smaller, alpha is equal to 10 degree, we are less than 1 degree. And if it's even smaller, we get a better approximation. So what I'm leading at, so we can take an imaginary line after 15. We say that after 15 we don't want to tolerate error, or we can even tolerate more than 1%. That depends on our experiment and our goal, basically. But we know that roughly 1% of the error is 15 degrees. So we can make this approximation. And this approximation leads to mg equal to omega square times L, because sinus alpha and alpha is equal alpha, and they cancel out. So alpha here, alpha there, they will cancel out. But the other thing that cancel out is the mass, as we know, as in the case of the free falling object. This is roughly a free falling object in one direction, so the mass will cancel out, and we are left with this equation here, which is omega is the square root of g times divided L, the length of the rope. From here, we remind ourselves about the pulsation, which is 2 pi over t, and we use this to basically solve for the period. And the periodicity is 2 pi L over G over square root. Why this is important? Because basically this tells us that the oscillation are synchronous, so the pendulum oscillates with the harmonic periodic motion when the angle is small. So it's a clock, basically. It can be thought as a clock. In fact, the first clocks were pendulum. And this is a good, let's see that this is a good formula for the time by doing dimensional analysis. So we know that the length is meter, and the acceleration is meter over second square, because acceleration, as we know, is the derivative of space over time square. So space over time square. And then there is a square root. So the square root will take the square root later on. So this will lead to the meter simplifies. The second square goes up, as we all know. So if we take the square root now of second square, we get seconds. So this is periodicity is in seconds, and this equation has the dimension of seconds. So we are good. We know that what we've done is correct. We have a solution for the equation of motion, which is an harmonic oscillation for small angles, with some approximation, of course. No frictions, no air resistance, and as I said, small angles. Okay, I think this is enough for the pendulum with small oscillation. We will get more in other videos. Thanks for watching. See you next time.